Starting again, there we go. All right. He discovered that whatever had penetrated the aluminum, the tin foil. Wait, no. Whatever had clouded the plates had penetrated the tin foil. He had discovered radiation. And in fact, radioactivity. Okay. And all radioactive events are exoergic. That means that these parts have less mass. This is probably good that I'm repeating this, right? These parts have less mass than the whole. Where did the mass go? They went into released energy. Next chart. There we go. In your note guide, right? So these are the types of radiation. An alpha particle, beta minus, beta plus, and gamma, and that's all we're going to look at. Okay? This is what it is. This is what they are. Okay? An alpha particle is fully 8,000 times more massive than anything else. It's just a big chorker, right? They're so big that an alpha particle you can essentially shield yourself with 4 centimeters of air, and there's not much to air. Okay?
On the homework, we were supposed to use helium as the alpha particle.
Yes, there you go. Helium nucleus. There you go. That's what it is, right? So it is basically 2 protons, 2 neutrons. It is ginormous. This is just a regular electron. This guy, a beta plus, is an antimatter electron. Okay, now remember, an antimatter electron is the same as an electron, except there's 2 important differences. It is positively charged, has the same mass, it's positively charged, and yes, just like Star Trek, when a positron encounters an electron, okay, they will annihilate and create pure energy in the form of photons in this case. And so you never actually detect beta particles in your detectors. You always detect the radiation of their annihilation, right? Which is always a pair of photons, and these are super duper photons. Each one has an energy of 500,000 electron volts. Holy cow. Yeah. Whereas visible light is like, a few electron volts, right? These things have 500,000 electron volts each. But yeah, there they are. Okay. And this is not terribly exotic. There's lots of antimatter particles. Why we're left with matter as opposed to antimatter, well, actually, that's the next chapter, right? And the short answer is we don't know. Or how do we know that we don't have antimatter, but what we call matter really is antimatter? I don't know. Okay. And then a gamma ray has no rest mass. It's just pure energy. It is a high energy photon, right? And this is the wavelength. If it's between 5 and 0.05 nanometers, we call it a gamma ray. It's fairly arbitrary. Okay. Alpha particles are stopped by air. A beta source, you can wrap in aluminum foil, thin aluminum foil, 1 to 3 meters of air, and a beta particle is all worn out. Okay. And then a photon, well, some thickness of lead is needed to stop gamma rays. Gamma rays have so much energy that they're actually used to sterilize beef, right? You have ground beef, which is, of course, ground beef is always dodgy because when you grind it up, you actually, the contamination is not on the outside, it's all throughout it because it's all ground up. Whereas a steak, all you have to do is sear the outside and you kill most of the E. coli. Ground beef, you've got to get the whole thing up to proper temperature to kill the E. coli. So one possible scenario is that you use a gamma ray source to sterilize the beef. So you load all the beef into a room, get all the people out, close the lead shielding, stick a gamma source that's carefully shielded in stainless steel or something like that, so that the material doesn't contaminate the meat, but the gamma rays blast the meat. You kill all the E. coli, and then you remove the gamma ray source and pull all the beef out, and it's sterile. Yeah. Have you made chemical reactions occur that maybe shouldn't occur? Maybe, we don't know. Is it safe? Probably, but maybe not. Right? Do you want to eat that beef first? I'll let somebody else eat it for about 30 years, and then I'll make that decision. Right?
How do you stop a beta plus particle? Or can you?
A beta plus, these guys just air. These don't last long because as soon as they run into a matter particle, they annihilate. Right? And then the question is, what happens to an alpha particle when you stop it? Well, it probably just picks up a couple of electrons and goes, hey, I'm helium. Right? In fact, that's where all helium comes from. All helium comes from the radioactive alpha decay, and it's in the atmosphere for as long as it takes for it to percolate up toward the upper edge of the atmosphere, the thermosphere, right, where it actually gets hotter. And on the edge of space, they gain enough kinetic energy to escape into space. So helium exists in the Earth's atmosphere in very low concentrations. All of it comes from radioactive decay, and we extract it, I believe, from the atmosphere using cryogenic processes. We condense it out of the air. Yeah.
So it
escapes into space. Yeah. Okay. Off it goes. There it is. Okay, so we discovered it actually in the spectral lines of the sun, hence its name. It is literally the sun element, helios, right? And then this is what happens to the parent nucleus when a alpha particle leaves town, right? You've lost 4 nucleons, 2 protons, 2 neutrons, 4 total nucleons, correct? Okay, they being the denizens of the nucleus. There was some book I read as a junior that talked about denizens, meaning like inhabitants of, right? Okay, so the mass number goes down by 4. The number of protons goes down by 2, and that's because you lose 2 protons. I don't know how to explain this without really sounding like I'm talking down to you. Beta decays, the key thing here is, remember, the beta particle, it's a bizarre thing. The nucleus manufactures this particle from pure energy. From pure energy, it creates the matter. Okay? We balance charge, you'll see that in a second, but the nucleon number doesn't go down. The nucleon number doesn't go down. We adjust the charge so the charge is conserved, and we'll talk about that in a sec, but the nucleon number doesn't go down. So it basically generates an electron from pure energy and spits it out. It's not like it's losing an orbital electron, it's actually creating an electron and spitting it out. This is a crazy thing, isn't that crazy? Yeah, nuclear energy levels pack a lot more wallop, yes? Just shifting around energy levels devastated Hiroshima, for example, right? Okay, yeah. So there's an incredible amount of energy stored in these things. There's enough energy to create an electron out of pure energy, and that's what's going on here. So in a beta minus, we are creating a negative charge. If we create negative, we must also create positive, and if we do that, then the charge is balanced, right? So what happens here is it's like a neutron crosses the aisle and becomes a proton. Yeah? That's like a House of Representatives reference. Right? There you have it, right? Okay, so it's like that. It's not what's really going on, but it's how you can sort of think of it in terms of what happens to the nucleus. So you gain a proton, but you don't change the number of total nucleons, right? And then if you create a positive charge, you've got to lose one somewhere, so a proton's got to cross the aisle and become a neutron. Its positive charge being carried off by this guy, yeah? This is a little bit crazy, isn't it? Right? And then the gamma ray, gamma decay, doesn't have charge. They're photons. They have no charge. They have no rest mass. So we don't change nucleon number. We don't change element number, right? Okay. So what happens? Well, basically, these things are usually tied to other decays, like a beta decay or an alpha decay, and all it is the nucleus blowing off steam. It's left in an excited state after the decay, and it's kind of like Tetris when you fill in a level and everything settles down. Yeah, you picturing that? Right? Think of all that energy that's released when it goes ka-chunk, like that, right? So the nucleus is left in this level, and things just drop, particles. There are energy levels in the nucleus. This is another thing to adjust your mind to, just like there are energy levels in the orbitals, right? And something is going from a high energy level to a lower energy level.
Do you have nail polish remover by any chance?
Nail polish remover, I do.
Because I know you use it to...
Yeah.
For his nail.
And for my nails. Et voila, mademoiselle.
Thank you, I'll bring it back.
Yeah. What are you using it to take
For the
nail
markers.
polish? For the markers.
Yeah.
Okay. Yeah. All right. So basically, and I can actually portray this, and I promise you I will portray this personally. Okay. But basically what you have before and after is you've got a daughter nucleus in an excited state, and it makes a transition to a less excited state. Okay. And I will act that out for you. But I don't want to do that right now because that'll like take away all the fun part about that. Yeah.
Where does the photon come from? Is that another like...
The photon. Photons are just pure energy, so basically it's the same place that it comes from, the spectral line, like the red line of hydrogen. Transformers, they could be, right? Here's a picture showing a magnetic field. Remember that an alpha particle is positively charged, and so of course if it flies out of there with that velocity, the magnetic field's into the page, the force is going to be that way. It's going to curve left. Electrons will curve because they're negatively charged to the right. And you don't always call them beta minus, they just call them betas. But the ordinary ones are beta minus. A beta plus would curve the left. It would curve the same way as this. It might have a different radius because it's got less mass. Notice that the alpha particle is not deflected. Why is that? Doesn't have charge, because remember charge, it's QVB is the force of a magnetic field. If Q is 0, then there's no force, right? So magnetic fields don't bend photons' paths. Gravitational fields do, but magnetic fields don't.